Okay, so while we are waiting for more people to come in, hi, for the nth time, my name is Nikhil Sontakke. I work as a principal engineer at Microsoft. I've been doing Postgres for a long time now, and I continue to get to work on exciting PostgreSQL technologies at Microsoft as well. This talk is about serverless. Like AI has taken up all the footage, man. I mean, serverless is a pretty exciting, architecture and technology. But everything is AI nowadays, and other things get pushed under the carpet, right? So in this talk, I just want to take you guys on a journey in terms of evolution of Postgres. Like, we have this monolithic architecture that Postgres has today, right? How can we evolve it into a serverless architecture? That's what we want to see, if that's possible. Do we have a clicker? With the USB. Okay, so here's the agenda for today. I'll introduce what we mean by serverless computing. What does that term entail? I'll also talk about why do we need it in the first place, right? Especially in cloud environments. Like, everything is cloud nowadays, right? So we'll look at why do we need serverless in cloud environments. And then, once we've done the basic definition, we'll drill down into database specific requirements, and then obviously get into the exciting stuff as to how we can evolve Postgres into a serverless version of itself, right? Okay, so this is like the standard definition for serverless computing. Wikipedia style definition. So it is a cloud native model, right? It is when we talk about serverless, we specifically talk about cloud environments, and it's a model that allows developers to run their applications without managing their servers, right? So if you look at a typical team, right, you'll have people who are working on the code. Then you will have an infrastructure team, which is responsible for managing all the infrastructure, and that's like the typical way of doing things. But if you adopt a serverless computing architecture, then the development team, the small startup that you have with very less number of resources, those people can focus on the actual app development, and they don't need to worry about managing the infrastructure, because that infrastructure is managed typically by a cloud provider, right? So this model allows the developers or a fledgling startup to just focus on their IP, develop their application, and not worry about managing the infrastructure at all. So how does this serverless architecture works, right? So I'm not sure if you've heard of this function as a service. Everything is as a service nowadays, right? So in serverless, we talk about function as a service, and in this architecture, what you do is you break down your business logic into multiple functional components. The components can interact with each other, and typically these functional components get fired via triggers, right? So I'll give you a very simple example. I'm a PGConf organizer, right? And I send emails to you guys pretty frequently, right? So sometimes we have to send 1,000 emails, or sometimes we have to send 10,000 emails, right? So what an example of a serverless application could be our PGConf emailing service, So when I or Pavan or Ashish, we come up with this email, dear speaker, this is your slot, we hope to see you, right? We come up with that template, and then we just click on a workflow, right? So that becomes the trigger, and that trigger is to send this email after replacing the placeholders to X number of people, right? So now if I have if I have to send a few hundred emails, I need a very small resource which needs to spin up, send the emails quickly and go away, right? But if I have to send 10,000 emails, maybe I need a beefier resource to be allocated, which can do the job efficiently and go its way, right? So when we talk about serverless, we typically talk about auto scale. Basically, depending on the requirements, resources will get spun up as per the requirements, and then they'll do their job and go away, right? And on-demand execution is the keyword here as well, right? As I mentioned, I don't want my email service to be running 24/7, right? It is only when I click on the workflow and I say send emails, it is then that the resource should be allocated. It should be a small, medium, high level resource based on the work I want to do. It should do its work and it should go away. So efficiency is built in because we optimize on the resource usage, and thereby we optimize on the costs, right? We all know that in clouds, costs is one of the biggest factors that we have to curtail or have a handle on, right? So yeah, what are the benefits of going serverless? I think now this is getting clearer, right? Based on the stuff that I've been saying, the teams can just focus on their work, right? I mean, our PGConf email service can just write that specific function, which is like, replace the placeholders and call send, right? Need not worry about, how it gets invoked and where it gets allocated, what if it doesn't get allocated? So, it need not worry about that. The cloud provider is supposed to take the responsibility for that, right? So that means obviously reduced operational burden. You now don't need a fully dedicated DevOps or like a infrastructure team. You can have one or two people who can effectively manage stuff from your end. And this pay-as-you-go pricing model, this is a buzzword, right? Everybody wants pay as you go. We only want to pay for that much usage that we do, right? It is absolutely critical to do that. So the earlier example was a pretty simple one. Now let's look at a little complicated example, right? So IPL cricket, let's say there's a mobile app or a website, or there might be Major League Baseball fans here. So MLB, IPL, similar kind of use cases. So typically you will have a mobile or a website, where you log in and you enter the app. And obviously during the peak season of IPL, you'll have thousands of concurrent users. Everybody's logged in. Somebody wants to watch the highlights of a previous match. Somebody wants to stream live data. Somebody wants to go to a discussion forum, right? Somebody wants to look at Virat's statistics. Okay, so these are different functional components that you could think of, right? And if you develop a serverless architecture, you could have functions for each of these activities. For example, you might have a function as a service to serve content, right? Video stream, live stream. You might have a function to work on the discussion board, right? You might have static images. You might have to connect to a database and run analytics, because people are asking what is the average for Virat in the last 2 weeks, right? So so that is where a backend as a service comes in, right? So depending on the functional requirements, you will either have like a static store, media backend, or you will have a traditional SQL database as a backend, And till date, this SQL database is, an instance which is running a single database server, right? And we have not had the opportunity to, consider, make any optimizations there, or see, if we can get the similar benefits of serverless with that database component, right? So let's see if we can see what might be the requirements of a serverless Postgres database. And obviously, this is all cloud specific, right? Because recall that serverless typically is, a cloud deployment model. So again, whatever were the requirements for a serverless app, I mean, broadly, you would expect the same kind of asks or requirements from the database side as well, right? So ideally, you want your serverless database to auto-scale without human intervention, right? I mean, you're not going to have a DBA who is sitting in front of a console looking at the spikes and saying, oh, I need to get my resource up or down. That doesn't scale, right? So you want auto-scaling for your database as well. And because it is a database, performance consistency is very important, right? I mean, you just don't want auto-scaling up and down and save money, right? You want your queries to perform with the same SLAs even when you're doing the dynamic auto-scaling, right? So performance consistency is very, very important. And obviously that means that, you need to intelligently adapt to the requirements, scale, and then do your stuff. Databases and HA and reliability is always a factor there, right? I mean, databases store your core data, right? And obviously you have to have it available reliably across any events that might happen in the cloud, right? So HA and fault tolerance and failure mechanisms and the usual still applies to serverless as well, right? So again, can we get pay-as-you-go with databases as well, right? That's a question that we have to ask. And if we can do efficient auto-scaling, then maybe yes, right? I mean, you could on-demand resize the resources up or down. And if there's a peak, you scale up. If there's a Black Friday or a Diwali sale event, your database needs to scale up as high as possible, give consistent performance, and then once the holidays are over, you want it to go to its baseline, right? So ideally, we want a pay-as-you-go model there as well, right? And now when we talk about cloud, we have these object stores, right? And they promise cheap and infinite storage, right? So basically what that means is that ideally your database solution should also be able to use these object stores for backup and maybe not just for backup, right? I mean, maybe even the live data or the resident data in the database could be stored there for cold storage and other requirements. So now I've laid down the ground rules in terms of expectations about serverless databases. They are pretty similar to what a regular serverless application might have. And now let's see if we can evolve Postgres and try to convert it into a serverless offering, right? So obviously a quick refresh about how things work in Postgres, right? All's well that ends in the wall, right? I mean, any traditional database, the implementation, whenever you do a transaction which makes modifications in the database, a corresponding wall record is generated which contains the changes truthfully. And when we say transaction commit, typically it is the wall that gets flushed to persistent storage, right? Postgres also modifies the data pages of the table itself, but those are flushed asynchronously, right? We don't want to have the performance penalty of trying to be synchronous with the data pages as well. Wall is sequential, sequential data writing off works really well. So that is what we do. So, and we all know that, physical replication is basically based on wall, right? What we do when we create a replica, physical replica, is we send the wall that's getting generated on the fly to the replica, and the replica just blindly applies that wall, right? So, I mean, wall is like the underpinning of every solid database. And I talked about the data pages, right? They get dirtied, but they are not flushed synchronously to disk. That typically happens via checkpoints. You know all about checkpoints, right? And I'm sure DBAs are always, wondering, how they can optimize and tune all the checkpointing parameters, right? Because checkpoints is a I/O intensive operation, right? You are trying to write the dirty relation pages to disk so that the wall records and the data pages are in sync at that checkpoint time, right? So yeah, checkpoint is one of the important thing that happens there. So okay, so let's start evolving Postgres now. So what are the first baby steps that we can take? So we have this cloud environment, and maybe the first thing that we can do is we create a shared wall storage server. So this is where we start talking about separation of Postgres as an architecture. So we want to come up with components. So we'll have a compute component, and you'll have a storage layer, right? So if we can have a shared wall storage service, then all the nodes in the system have a single source of wall now, right? So all the primary node and the multiple replica nodes have access to the same shared wall storage service, and they can just apply locally on themselves. So this also maybe makes failover simple now. I mean, we have a lot of solutions for failovers, and typically the failover solution tries to look at a replica which is closest to the primary that is going away and tries to promote that, right? So it does a lot of checks in terms of LSNs, and quorums and a lot of stuff, right? But now in this case, because all of the nodes are sharing the same shared wall storage service, maybe failovers are simpler. You could, in theory, promote any replica in case of failover, and it will quickly apply the wall that has been generated so far before it becomes the primary. Yeah, I'm getting there. Yeah. So then let's ask ourselves. I mean, is this serverless? Does it look like it, right? Why? Because the question that he asked, right? Every node still has a complete copy of the database, right? So you manage to get the shared wall service separated, but all the nodes are still applying or generating that wall and creating a full copy of the database on itself, right? So this doesn't look like a scalable serverless kind of a solution, right? So that means we need to evolve this further. Okay, so what's the next logical evolution that we can do? Okay, yeah. So yeah, you guys are getting it, man. Good. So so yeah, I mean, we managed to get a shared wall storage service going. Now let's see if we can have a shared relation page storage service, right? So instead of now every node having a copy, can we have an architecture where there is shared wall and there is shared rel page storage service, right? I call it RS and WS, from time to time. Yeah. So again, before we get into this, let's again go back to walls, right? So in Postgres we have this thing called as LSN. So what is LSN? LSN stands for log sequence number. So recall I said that when you do a transaction, the wall record is generated, and that contains the entire change that has happened, right? So every wall record gets an LSN attached to it. So LSN is basically an offset in the infinite wall stream that we have, right? So it will say at infinite 1 million bytes from the start, this is the wall record for this change, right? So that becomes the LSN of that specific wall change. And when that gets applied to the page, every rel page in Postgres, typically it is 8 KB in size by default, right? Every page has a page header, and it contains a field called as PD LSN, which is the LSN of the latest change that happened to that page, right? So when the transaction is committed, that LSN gets attached to that page that was modified in that transaction. So like drilling down further now, I mean, can we just have one image of the relation page in this rel page server? I don't think so, because we still have the situation where, let's say the primary is running, has generated wall up to L1, LSN L1, and replica has a lag, right? So it's running at an LSN which is less than L1, right? And now, because the pages are not available locally, if any compute node wants that page, it will make a request to the rel page server saying, hey, I need this page at this specific LSN because I'm running at this specific LSN, right? So now if the replica is lagging behind and it makes a request, it needs to see that page at that earlier LSN, right? So this means that a page server will now have to store multiple versions of the same page, right? So as long as there is a request for a page at an earlier LSN, you will have to store that version. And obviously when the system moves ahead, right, when the replicas have caught up, then you can remove that older page version, right? So now in this case, where will the checkpoint happen? The checkpoint doesn't need to happen on the primary. The checkpoint will now, the activity which we call as checkpoint, will now happen at the rel page server, right? So basically, the primary will generate wall. It will go to the persistent wall storage service. The wall storage service will send those walls to the rel page server for redo, and checkpoint will happen on the shared rel page server, where it will actually convert the wall pages into multiple page versions at different LSNs, right? Makes sense, right? I mean, if you think of it logically. So just focus on what we achieved here, right? No checkpoint needed on primary. I mean, that seems to be like an awesome change that has happened, right? I mean, when I said some time ago, right, DBAs, tear their hair, tuning the checkpoint parameters, adding delays, trying to be more aggressive, less aggressive, trying to, it's a losing battle, right? Every time you want to write the maximum number of dirty pages to disk so that, the LSNs can move forward, you could recycle the wall and stuff like that. But now with this architecture, because you're not doing any checkpoint on the primary, it seems like an amazing win to me, right? Performance wise. I mean, database traditional bottlenecks, IO and CPU, right? Here it seems we are taking care of IO pretty well. So in terms of like in this architecture, now the primary and the replica nodes can be very, thin. They can be very thin, because when they start up, they just need like a basic subset of the PG data contents, right? They don't need like the entire relation pages. They only need the basic set of files that are needed to start, right? So for the configuration parameter file, PostgreSQL.conf, the starting system catalog information, the SLRU transaction visibility information, rel maps and other auxiliary files, and typically that's going to be a very small tarball basically, which needs to be sent to the nodes to start up, right? And again, in this case, typically again, it's all tied back to checkpoints. So in traditional Postgres, when we do checkpoints, the first change that happens to any page after a checkpoint, it saves a full page image of that page into wall before it makes the modifications, right? That is why we have this full page write parameter, right? And we need to do it because file systems have typically a smaller atomic chunk write size, right? Recall our pages are 8 KB in size, and traditional file systems can do atomic writes at 512 bytes or 1024 bytes, right? So a single 8 KB page write needs multiple file system calls, and that's why we get into these issues of torn pages, and that's why we need full page writes. But now here, if you have a dedicated vault storage service and a dedicated shared real page storage service, then the primary doesn't need to do full page writes, right? So again, we don't even need full page writes now in this architecture, right? So this is another pain point that we have removed in terms of I/O in this architecture, right? So you will generate much less vol compared to traditional Postgres here, right? Because these full page images are like basically you're just doing like a taking the current 8 KB contents, putting them into vol, and then doing the modifications, right? So it's pretty I/O intensive, and it generates a lot of vol. So so these are like the salient points that we can discuss about this architecture, right? Now what happens is the replica compute nodes can be created much faster, right? So it's very easy to spin up multiple replicas, and in theory you might be able to support more replicas performantly now in this architecture, because otherwise earlier if you have a lot of replicas, then the primary has to send vol to all of those replicas, or you'll have to do cascaded replication and very complicated stuff. Right now in this thing, you can just quickly spin up a replica with a small basic subset, and it's good to go, right? So this also means that there will be typically lesser lag vis-a-vis traditional Postgres deployments, because again, primary and replica, the replica node just needs to replay the vol for the pages that are in its shared buffers, right? It doesn't need to create a local copy now, right? So that again is a big win, and because of this, the replicas will typically stay up to date with the primary. Yeah.
This checkpointing in full page write all here have one more purpose of recovering faster, for recovering correction less complex.
Right.
So with the checkpointing, we are going with the storage level. So how the checkpointing will work in the recovery schedule? Because right now,
yeah.
making the performance faster, but what on the recovery front?
Yeah. Let me complete the slides, and maybe we can come back to that question as well. So other salient points: faster recovery across compute node restarts. Right. Traditionally today, if PG restarts, it finds the last checkpoint and it redos the the vols from that point to come up to date. Now here in this case, again, it just needs the basic subset, and it can identify the LSN that it needs to work with, and then just say to the rel page, give me the page view at this specific LSN, right? So restarts have become really fast now in this architecture. And this also now allows you to do fast branching or cloning of your database, right? So these technologies are now very well developed at the storage layer, right? So let's say if you want to clone a database, what you can do is you can at the storage level just take a snapshot, right? Which is like nearly instantaneous nowadays based on the technologies that we have, copy on write or other fast snapshots that all these cloud providers provide, right? So in this case, if you want to do a clone, you just basically do a metadata operation saying clone or snapshot, and then you can spin up another serverless this kind of an architecture elsewhere using that snapshot, right? You can also do branching. Yeah.
So like the primary and the replica is hitting the same shared server.
Yes.
Storage.
Yes.
And what about the I/O? Like it will be I/O will be instancing on the same file system, right?
So as I said, the primary and replica now basically act as database caches, right? Whatever data they have in memory, they will work with that, If they don't find any specific page, then they will request the page server. And once it comes there locally, they will just continue to work with that, right? So you'll only be going to the page server for pages that don't exist in your cache. Yeah.
It will be a single point of failure, right? Storage. So if it goes down, then both primary and secondary.
Yeah, so I mean, you will still need HA for the page server as well, right? So there are like multiple ways of doing that. So yeah.
Like taking the HA from before the compute and putting it after the compute.
Yeah, I mean, like traditional, yeah, I mean, as I said, the traditional architecture, you have a primary, you have 3-4 replicas, then you have to set up Petroni, you have to set up everything. Here now you will maybe have one component, and you can have a robust HA for that, right? So we can maybe discuss this more as as we go along as well, right? So yeah, I mean, again the question, I mean, are we like getting towards serverless? What do you think? It's like maybe some evolution seems to be happening, right? So yeah, let's see if we can do some more stuff. So yeah, I mentioned about object stores earlier in the serverless app environments, right? I mean, here also now what we can do is, like, because you have a rel page storage service, you are free to choose whichever database layout you want, right? I mean, if you want to work with an object store, then you could have like a big sized blob of data which can contain your actual data pages, or you're no more tied to the database layout, like 1 GB segments of each relation and so on and so forth, right? You are basically free to use any backup strategy that you want to use, and depending upon the object store that you're working with, you might want to have a strategy that works best for that. So typically when we talk about object stores, we think of blobs, right? Page blobs, byte blobs. So maybe the data from Postgres can now be mapped into blobs in the object store. And now because you have access to object stores, you can get cheap and limitless data storage, right? I mean, this is another pain point that customers talk about, right? I mean, our backups are eating up so much space, we are not able to manage them properly, or you have to set up again complicated stuff. But with object stores, everything is taken care of. Redundancy and other things are also taken care of there, right? So some time ago, somebody asked a question like as to what happens in case of restarts. I mean, obviously this is software, right? Even they can crash, right? So here, instead of having a complicated HA system at the upper level, now you can focus on HA for these specific components. So even like a traditional having a standby for the rail page server, which is actually just like getting the same wall from the wall storage service and applying it locally, even that works, right? And you might even have data stored in the object store, right? So in extreme cases, when the restart happens, they can quickly reseed themselves from the object store, right? So that's also possible. And these object stores are now evolving in terms of providing bulk APIs to get like a large amount of data in one shot, fast enough, and then you can work with that locally, right? So another pain point in time recovery, right? So point in time recovery means that let's say you were working on your database and somebody does like a drop table unintentionally, right? I mean, he or she assumes they are working in the test database, but they run that on your main database, right? So you want to restore to a point in time seconds before that command was issued, right? That is called as point in time recovery, right? Now in this case, because the rel page can store multiple versions of the pages, theoretically you can have all the versions of the pages possible, right? And you could put them on object store, cold storage. So this means that even that with this very fast PITR is possible, right? You can basically say to the rel page server, give me all the pages till this point in time, right? And it can use the metadata of the storage and basically start returning pages from that version, right? So, even point in time recovery becomes pretty fast and efficient with this architecture. And this is another thing, right? I mean, some customers want geo-distributed backups, right? And now again, it's like a very, bulky thing to set up at the database level. But now with data going into the object store, the storage layer itself can do it automatically behind the scenes, right? And again, all of this is going to be very cheap and efficient to store. So yeah, serverless. It seems like we're getting there, right? I mean, all like recall the initial bullet points I talked about serverless and the requirements. It looks like we are slowly moving there. So let's evolve it further, right? So now it's possible that once you have this rel page storage service, you could actually have multiple primary nodes using that same page server, right? So this is what is multi-tenancy, right? You could have a tenant ID for primary 1, unique tenant ID, and another tenant ID for primary 2, right? And all the pages for those tenants are within that namespace in the page server, right? So every query that comes will say, okay, give me the page inside this tenant ID, right? So this ways, you can easily get multi-tenancy with this architecture, and a single rel page server can work with multiple tenants, right? Obviously, this wouldn't have been possible at all in the earlier architecture, the monolithic architecture. Everything is tied to one instance, right? But now here you can have multi-tenancy. Sharding also, becomes interesting. This is the other way around, right? You could have multiple page servers, and then the primary could shard across these multiple page servers, right? So you could have a sharding algorithm which says, very simple logic you could use, or you can go as fancy as you want, right? You could say, okay, my 1 GB segment, first 1 GB segment goes to rel page server 1, the second 1 GB segment goes to rel page server 2, and so on and so forth, right? And now this with this, you can get the benefits of more, parallel IOPS. The queries can happen to the multiple page servers, and you can get efficient sharding and data scaling that ways with this architecture as well. So yeah, again, I think we are running out of time. So we just wanted to quickly, say, are we there yet, right? What do you think? I just wanted to highlight whatever we've discussed so far. We have managed to separate Postgres into compute and storage components, right? The storage components was further diversified into the wall service and the page service components. Because of this multi hey, what's happening? I just wanted to show since we have multi-tenancy now, it's possible that if this primary is not being used, you can essentially bring this node down to 0, right? So now you're getting into that model where you start paying for whatever you're using, right? If there is no activity happening here, the pages belonging to this can be shifted into the object store from the page server, and when it comes back, you can get them and start working again, right? So, and also now because this is mostly a compute node, you can do dynamic resizing as well. You can, based on the requirements during Diwali, this could be a beefier resource. In other days, it could be less. If you go viral for whatever reasons at any time of the year, this will just can scale up and down after you are done with your viral phase. So stuff like that now becomes possible with this architecture, right? So yeah, this is what I meant, but compute nodes can now scale to 0, right? So only those compute nodes which are active, they can get used. And obviously, you now have cheap and limitless backups in object store, or even your traditional database data can be stored there for reseeding purposes. Even effective sharding and multi-tenancy seems possible. We looked at the architecture, right? So obviously HA, there was a question, right? You have to have HA in place but here in this case, you could focus on doing HA for the wall storage service and the rel page storage service components, right? We now know that it is easy to restart or it is easy to deploy new nodes, because they contain a very small subset of the data. You just start with them, and as long as they can specify the LSN they are working with, the page server should be able to serve all the requests for them, right? So yeah, I think it's pretty difficult to get into like the full-blown traditional serverless app kind of a usage. But with this architecture, I think we have most of the points covered. I hope you guys agree with that. And what we can do in the future, right? We could even like look at multi-write compute nodes, right? So the same, you could have multiple maybe primaries if you want to call them for the same database, right? So the tenant ID remains the same, and you could use something like a global lock manager. So yeah, you could have like a distributed global lock manager or some mechanism to see if people can do writes in parallel, right? So I mean the possibilities seem achievable with this kind of an architecture, right? And this is a very hot and happening space, right? Cloud infrastructure continues to evolve. You've looked at a lot of us talking about how we allow resizing or instantaneously both at the compute and the storage layer, right? So this architecture can now get benefits of that as well. Yeah. And yeah, I mean to me at least PostgreSQL seems to be on track for cloud native kind of deployments, right? I mean obviously I have deliberately not talked about any existing architecture or any existing deployments out there, but there are obviously some. But I think with this architecture, it's like a good blueprint to go serverless. Yeah. Okay. Thank you. I think we have time for a few questions. Okay. Yeah. Yeah. Please.
There will be two questions. First is that when you say serverless deployment for the Postgres, so do we have extensions available? Extensions in the sense AGCLI extensions or the PowerShell modules or Terraform extensions? I'm talking about the automation point of view.
Yeah, so I mean the main key thing I mentioned about serverless is you need not worry about this cloud things, right? I mean they will be taken care of by the cloud provider, right? So, and yeah, so those they will provide you all these tools, right? So yeah, so those will be available. Yeah.
And the second question is that the architecture which we discussed for having the shared storage or the shared service, shared services.
Mm-hmm.
So just like Azure SQL, Azure doing same thing for the Microsoft, for the SQL Server and the Azure SQL services. They do all these things behind the curtain.
Yeah.
Setting up all these things, just I have to select the high availability and the number of replications depending on the location. We set the synchronous and asynchronous in between that.
Yeah.
So why don't we push all these things behind the curtain?
That is what will happen eventually, right? I mean once we get like a solution like this, and the customer wants this kind of a solution, that is what exactly will happen. So the interface will remain the same, and at the back end you will get all of these goodies.
For me, it is just like a
Exactly. Yeah.
resolver or the load
Yeah.
balancer.
Yeah, you got it. I mean that's what we would want to do eventually. Yes. Yeah. Okay. All right. Thank you. Yeah. One more question, I guess. Yeah. Yeah, I mean, I mean, Microsoft continues to do a lot of research, right? And this area is ripe for disruption right now, and there is a lot of research and POCs and stuff that's happening around this inside. Right.
But we want to see how it can be scaled into a server.
Exactly. Yeah.
We want to contribute. That's why I just asked.
Yeah.
Can we get the slides?
Yeah. They'll be uploaded to the website. As I said, this is just like a generic evolution, right? I mean, it is nothing specific to any startup or any company, right? I mean, this is just like a logical evolution of Postgres from a monolithic backend into a serverless architecture. Yeah. Okay, thank you very much. Thank you.